I am Matt. I'm from Airbnb, and here to talk specifically about two competing applications of non-parametric inference in the context of detecting significant improvement or regressions in page performance. This is me pre-pandemic. It's probably time for a new headshot. But I've been at Airbnb for a few years now, and my work is in three areas primarily. The first is characterizing complex guest behavior, understanding guest flexibility, repeat visitation patterns. The second area is understanding page latency and how that impacts guest success. And the third area is just experimentation theory and strategy and tactical execution. I'm going to be speaking specifically about those second two areas that I mentioned, so page performance and experimentation, connecting those through the lens of non-parametric inference. So rather than read through this full abstract, I'll just give you the background that in listening to other people talk today and hearing about some of the deeply cutting edge and novel concepts that they were sharing, I don't think that any of the things I'm going to be sharing today are deeply novel, but I do hope that by revisiting some of the more fundamental concepts or foundational aspects of ML, or at least statistics, we can start to realize that sometimes a simpler approximation is a better answer to a question than a more comprehensive, exhaustive solution. So specifically, I'm going to start with a little background and problem, talk about the page performance score at Airbnb, the challenge of PPS inference, before going into a solution and discussion around this challenge, specifically around the concept of revisiting the null hypothesis itself, and talk about some results and benchmarking with respect to what happens when we do that. All right, so the page performance score at Airbnb is a way that we quantify the performance or the latency of a page through several signals, from rendering time to interactivity delays. These are 4 of the 5 kind of subcomponents that I can easily show visually on a slide that represent some of the key milestones that we track when it comes to measuring page performance. So something like time to first contentful paint would be how long does it take for something to render on the page. Time to first meaningful paint is also a rendering milestone, but it's basically going to be how long does it take for the hero image or the most computationally intensive component above the fold to render on the page. We also, as I mentioned, have some of these measures like interactivity delays that we're interested in. How long does it take between tapping on a button to the browser or the app being able to respond to that input? That's first input delay. And then finally, before I'm able to show visually here, we have this notion of total blocking time, or how much is the total time that the main thread is blocked while trying to be performant and basically run the app or the browser. The fifth one that I can't really show here is what we call cumulative layout shifts, and it's basically a measure of the visual instability that a page experiences from one frame render to the next, and we basically want to keep that very low. So obscuring the exact math a little bit, the page performance score is basically P95 for each one of these metrics measured for a given population over a given window of time, whether it's an experiment or just a single day's data point. Mapped via a scoring function from a number from 1 to 100, reweighted through some weights, add it all up, and that gives us our PPS, page performance score, from 0 to 100. So it's a very kind of strange aggregate, mishmash together concept, and we're interested in understanding in the context of a A/B test, for example, how we can measure a difference between group A and group B on this aggregate, complex, weighted metric. I kind of skipped over some of the math here, but basically that function that I mentioned for each one of these subcomponents just basically maps the actual millisecond value for wherever that milestone might be to this score from 1 to 100, and then we do a little reweighting to get everything into that 0 to 100 range for the overall PPS score. So the specific challenge of PPS inference is that this is a weighted aggregate function of multiple underlying distributions, and we can't necessarily say that it's going to satisfy assumptions of normality. So Welch's t-test, which is frankly the classic parametric approach that is the backbone of our experimentation infrastructure at Airbnb for a lot of A/B tests, it's not necessarily appropriate. So the solution here is non-parametric inference methods. And for a quick refresher on why non-parametric methods are valuable, here's a quick comparison, not necessarily of what I'm going to talk about, but just some context. If we're interested in detecting a true difference between groups in normal data, and we attempt to use something like a Mann-Whitney test, a non-parametric kind of rank test, or a classic parametric approach, like I mentioned Welch's t-test, we can see that they're pretty evenly matched, depending on, independent of sample size, pretty evenly matched across a range of true deltas that we're attempting to detect in our data set. The situation changes, however, when we start looking at something that's not normal. When we start investigating log normal or other kind of distributions, we can see that the Mann-Whitney test, the non-parametric approach, substantially outperforms the parametric approach in this case. This can mean up to 1.3 times greater power, or put another way, it means that our minimum detectable effects are much smaller. So that brings me to the idea of bootstrapping, which is a classic non-parametric approach. The idea being that we have two groups. We compute the parameter of interest that we're interested in, here shown by theta, but let's call it delta, since I'm going to be referring to it as delta in other situations. We then basically try to construct a null distribution. We have a null hypothesis that says that all of these individuals that have been assigned to this test should be fundamentally similar in the null universe, the null distribution. So we're just going to discard their group labels, put them together, shuffle, resample with replacement from this group, recompute this sort of bootstrapped or null set of parameters of interest, do this many, many times, and compute a p-value by basically looking for the set of simulated data sets in which the parameter, the bootstrap parameter exceeds the initial parameter. So let's talk about what happens when we actually revisit that null hypothesis. So again, if we have only one observation per randomized unit, so maybe this would be like the height of an individual, this is still a pretty trivial, easy problem. We just do exactly what I described. We discard the group labels, group everyone together, sample with replacement from this collected group, and recompute our parameter of interest. But what happens when, as is the case with a lot of performance data that we have in our experiments, we have many units of observation per randomized unit? Well, in this case, if we try to maintain this sort of latent structure of the data, or maintain the notion that these performance events belong to this user, even if we discarded the notion of a controller or treatment group for those users, this is what's known as cluster or block bootstrapping. Again, not deeply novel, just kind of renaming it strict bootstrapping for the purposes of this presentation. But if we go back to the concept of the null hypothesis itself, and we say, well, if all visitors are fundamentally similar, when we start to group them together, shouldn't all of the attributes, or in this case, the performance events that are generated by these users, also be fundamentally similar? And if that's the case, then we should be able to sort of just resample at the performance event level rather than the individual level or the randomized unit level. So when we do this, it's quite clear that the lazy approach is a much simpler algorithm to implement. It's, given the kind of assumption I made about being able to relax the null hypothesis, I would say that it's questionably valid, which I'll get into in a moment, but it's definitely faster. The strict approach is a little bit more complex to implement and establishes valid, but a little bit slower. So there's a trade-off to be considered. So I want to emphasize these 2 points, questionably valid and slower. Specifically, when I say that the lazy approach here is questionably valid, it's actually just a simpler classic interpretation of the basic bootstrapping approach developed in kind of the earlier days of the ML statistics community. It's just a little bit more assumption-free than the strict version. So when I say questionably valid, what I'm actually meaning when I say that is that it's actually potentially overly conservative given the underlying hidden structure of the input data that we are choosing to ignore. In other words, we might have an amplified false negative rate. While the strict algo was formalized and explored a little bit more recently, again, this is basically just cluster block bootstrapping. This was designed as a way to maximize power by controlling for within subject variation during construction of that null distribution. So from a practical standpoint, at Airbnb at least, we have an abundance of latency data in typical experiments. So the real world value of the strict algo, maximizing power for us, is pretty minimal at best. Our primary concern has always been to minimize false positives rather than false negatives. So for us, frankly, the overly conservative method should suffice. And because that's been mostly kind of theory and conjecture up to this point, I wanted to give you a sense of, with an actual A/B experiment, what the data ends up looking like in terms of what the null distribution looks like specifically. And you can see that strict null distribution is a little bit more kind of tightly coupled near the middle there, while the lazy null distribution has a little bit wider kind of symmetrical noise injected into the tails. In this case, you can also see the true delta is very clearly in the tails of the distribution. So regardless of the reference distribution that we use to try to determine if this is significant or not, we're going to get the answer that we were hoping for: significant regression in the page performance score. So in closing, I think that I'd like to return to this quote by George Box, or at least repeated by George Box many, many times, which is that all models are wrong, but of course some models are useful. And keeping this in mind, I'd like all of us to maybe come away from here with a few conclusions, one of them being, what is the incremental value of a more precise answer to my question? When does it benefit me to really, really apply the strictest, most comprehensive, exhaustive method versus one that'll get me most of the way there? And then finally, I don't know how to go back, but the second one was, what is the practical, real-world value of answering my question with a stricter method? In both the cases that I showed at the end there, it was quite clear, regardless of the method that we choose, that there had been a significant regression in page performance. So if you've got a clear answer from an approximate method already, maybe it's time to start focusing on other more pressing questions. Oh, thank you for going back. Appreciate that. The final note I would make is I just want to close with some gratitude to the conference organizers for having me, to you all for listening to me, and to everyone at Airbnb that contributed to this work. Thank you. Any questions? Yes.
Can you talk more about the latent variables that you have?
Yeah, sure. The latent variables that I had specifically.
And how it impacts the null hypothesis?
So it really depends on the underlying structure of your input data. So again, if you have only one observation or close to one observation on average or on median per individual, you're not going to get much kind of speed up from using that lazy approach. The speed up is much more pronounced when you have many more observations that are, within individual that tend to have common variance, I guess. Any other questions? Yeah.
Do you use some metadata like the location, or I don't know, even for an individual, it might be a different pattern versus other individuals. So do you use those type of data to kind of customize?
That's a great question. We certainly store all of this metadata, but haven't started really mining or attempting to inject that layer of information into this inference method to, again, make it more and more precise. In general, I think I'm more interested in taking precise answers and finding an approximate solution that is almost as good with much less compute time.
Thank you.
Yeah, sure.
Any other questions?
When you were comparing the two methods, I saw like a table that you showed that seems to indicate, I think it's as the number of samples maybe gets bigger, the speed up seems to become smaller. Is that the general trend, or is it like a random?
Good question. So that table was actually with respect to the number of iterations just in the bootstrap loop, just showing that this isn't simply an artifact of like small number of iterations. It sort of steadies out and scales. I think the factor was like 1.3x speed up at small kind of loops. Larger loops would be still about a 1.2x speed up. In general, sample size of an experiment, and again the sort of within experiments typical number of performance events generated by a given guest, that will strongly influence how much speed up you can get out of this as well.
A little tangential to your main topic, but when you where you're computing the PPS score, right, as a combination of the five subscores, right?
Yes.
And then it seems in the method you are actually going back to looking at those individual ones to figure out this in this non-parametric method. So I was wondering if there is a way to not combine the PPS, the 5 scores, and get to the PPS and then go back. Is there a way to combine the original 5 and look at it directly and try to say what the page improves?
That's a great question. I mean, given that my talk is conceptually about approximation when it's appropriate, going a little bit further and saying, why don't we just look one component at a time, understand those distributions and if they've improved or regressed, and then you have the answer to your question as well, potentially with an even easier kind of output than, like as an example, if we were to switch from P95 for each one of those subcomponents to an average, we'd still be capturing key information about the tail of that distribution for that subcomponent, and we would be able to shoehorn it into a parametric method a little bit easier. We do that, but sometimes we have situations where we have interactivity improve at the expense of something like rendering time. So then the business leaders tend to be very interested in, well, look, like I know this is up, this is down, conversion sideways. Tell me, did the page improve according to our latest definition with the appropriate weights that we have for each of these subcomponents? Cool.
Any other questions? No? Thank you so much, Matt. Great
Thanks.
presentation.